relax and stop me any time if you have any questions. Okay, so we'll start with recalling some very well-known things about 3+1 dimensional black holes, and then recall some results about stability of black holes, both as solutions to the vacuum Einstein equations. And I will also consider a particular matter model, which is the Einstein-Vlasov equations. In the second part, I will then present to you some higher dimensional black hole solutions and try to tell you a little bit about what we know about the stability, what we expect about the stability of these solutions. And I will try to also tell you how one can start by studying linear fields on these fixed black hole backgrounds and then try to understand more advanced and complicated stability properties of these solutions. So among higher dimensional solutions, I will focus on the case of 4+1 dimensions. So just one dimension higher than the usual black hole solutions that you all know. Okay, so we are interested. I should also say that everything I'll say will be classical, and I will restrict to the case of zero cosmological constant. Okay. Okay, so we're interested in the stability of the black hole exterior as a solution to the Einstein equations that you see on the slide. And let me remark that these equations can be formulated in dimension greater or equal than 3+1. So for me, n will be the total, the full space-time dimension in the rest of the talk. So as Soon-Jin reminded us at the very beginning of the conference, the Einstein equation admit a locally well-posed initial value formulation, which provides the mathematical framework to study the dynamics of solutions from the point of view of evolutionary PD. So if you want, for an evolutionary PD perspective. Okay. Now let me start by looking at the special case where the energy momentum tensor T is identically vanishing and the equation reduced to the vacuum Einstein equation reaches G equal to 0. So as we all know, that meet explicit stationary asymptotically flat solutions that I list on the slide. So the simplest solution is the trivial one, the flat solution called Minkowski space that was originally formulated by Minkowski in the context of special relativity. The simplest non- Yes. Yes. There's a green light, so I can assume green light, assume it's on. Simplest non-trivial solution is Sfarchi's solution formulated right after the original formulation of general relativity by Sfarchi in 1916. And then we have a more complicated geometry called the Kerr solution, discovered much later in the 60s in 1963. And we know that one very interesting property of Sfarchi and Kerr is that they describe black hole solutions. So I'll very quickly recall some properties. This is the Sfarchi solution in Sfarchi coordinates. Sfarchi solution is really a one-parameter family of black hole solutions parameterized by parameter m, which I will call the mass and assume will be greater or equal than 0. This is a family of static, spherically symmetric, and asymptotically flat solutions, which embed as a dm equals 0 member of the family in Minkowski space. And let me also recall a remarkable, important property of the rigidity property of this family, namely the fact that any spherically symmetric solution to the vacuum Einstein equations is isometric to Sfarchi solution for some m, for some mass m. In particular, this implies that spherically symmetric or spherical symmetry implies no dynamics in the vacuum case. Okay, and this goes under the name of Birkhoff's theorem. Now, the Sfarchi family sits within a wider, more general family of rotating black holes that is called the Kerr family. And again, the metric is explicit. You see here on the slide. It's a two-parameter family of black hole solutions with parameters A and M. The Stoker will take A in the subextrema range strictly less than M. So this describes a family of stationary axisymmetric black holes, which are again asymptotically flat. And for A equal M equals 0, the matrix formally reduces to Minkowski space. And the family embeds the Sfarchi family as the A equals 0 one parameter subfamily. Here, again, there is a rigidity property, which the way stated on the slide, it is a conjecture. The n is smooth stationary and asymptotically flat solution to the vacuum Einstein equation is isometric to curve spacetime for some A and M. Okay. Now let me recall the very few some of the nonlinear stability results that we know about these solutions. So the nonlinear stability of Minkowski space, again, we heard about this in Sunjin's talk, was originally proven by Christodoulou and Kahneman in the 90s. What about black hole solutions? So it turns out that with very few nonlinear stability results for black holes, in the A equals 0 case, meaning in the Schwarzschild case, there is a proof of nonlinear stability of Schwarzschild by the Fermat-Sotzeke, Rodinsky, and Taylor, which characterizes all small vacuum perturbation on the given Schwarzschild solution, which eventually converges to a possibly different Schwarzschild solution. So let me remark that if you consider a general small perturbation of Schwarzschild, you expect that the evolution of the perturbed data will converge to a slowly rotating curved black hole with mass similar to the original mass of the Schwarzschild black hole. So in this sense, the problem of nonlinear stability of Schwarzschild has, in a sense, to be understood already within the curve family. And because of the rigidity result that I mentioned before, Birkus theorem, the problem also has to be understood when in vacuum. It has to be understood outside of spherical symmetry or any other 1+1 dimensional reduction. I would also like to mention previous work by Kahneman and Sheftel in polarized axis symmetry, which is a 2+1 dimensional reduction of the nonlinear stability problem for Schwarzschild. In the slowly rotating regime, there's a series of papers by George Kahneman, Sheftel, and Shen proving nonlinear stability, whereas the full resolution of the nonlinear stability problem in the full subextrema range remains to be done in future works. So in the next slide, I'll summarize quickly the steps of works that led to these results that you see on this slide. But before moving to that, let me emphasize that the curve metric can also be considered in the so-called extremal case, where A is equal to M, which one expects a very different picture from the one that I alluded to in this slide, which is as interesting as the one that I'll be describing in the subextremal case, and about which you will hear, I think, in talks and also in the last talk analysis lecture, if I understand correctly. Okay, so this gives me the opportunity to sort of move to the next slide about the subextremal case. So this is, if you like, a very condensed presentation of what has been the roadmap towards the understanding of this stability problem. It's a body of works from the 60s and 70s from the physics literature on the linear mode stability of black hole solutions, in which, together with showing linear mode stability, there also present some ideas and insights that remain very central in our more modern and today's more mathematical approach to the problem. And I'll mention one in a minute. However, to prove nonlinear stability of this solution, one needs a more thorough understanding of linear stability. So as the first step, one can look at the wave equation on fixed black hole backgrounds and prove decay for general solutions to the wave equation. And I've reported here some contribution towards this problem. There's also been works about the precise asymptotics of waves on black holes, which also are interesting. And I've only sort of mentioned, again, some of these works, but there are many others that I'm not mentioning here. The second step is understanding solutions, black hole solutions, stability of black hole solutions as solutions to the linearized Einstein equations. And I've reported here some works. I want to recall that most of these works, they build upon an idea which is actually presented in Tarkovsky's work, namely the fact that the system of linearized Einstein equations can be formulated in such a way that two of the linearized quantities present in the system, which are in fact linearized curvature quantities, they're gauge invariant and exactly decoupled into two wave-like equations, which are called Tarkovsky equations. So this gives you the opportunity to analyze these two quantities separately from the rest of the system, But then to employ or to apply linear stability result to the nonlinear problem, you also have to control and approach the rest of the system and control the gauge-dependent quantities in the system. So this is sort of the complete linear stability problem for black holes. So together with these linear models, another interesting model is that of studying nonlinear waves on fixed black hole backgrounds. So there are works also in this area. Here I've only mentioned a very recent one about the Fermi-Rodiansky and Taylor looking at quasi-linear waves on fixed curve backgrounds in the full subextrema range. Okay, let me emphasize again, there are many more works than the ones I've stated on this slide, but because I want to get to the high dimensional case, I will sort of leave you with these references. Okay, so this was the case of the Einstein vacuum equations. Now I want to say something about the Einstein-Vlasov equations. And there will be a non-trivial overlap with Jacques that I should thank. And so you see a summary of what Jacques explained in a more sort of detailed way. So the Einstein-Vlasov equations, they govern relativistic collisionless many particle systems. And they are formulated like the system that you see on the slide. So you have the energy, you have the Einstein equations with energy momentum tensor. When the energy momentum tensor, you see F, there is a non-negative distribution function which depends on position and momentum variable, and this transported along the geodesic flow of the manifold Mg, as encoded by the relativistic Vlasov equation, which is the third equation appearing in the system. So X is the generator of either the null geodesic flow of Mg, and this will give you the massless Vlasov equation, or the generator of the time-like geodesic flow of Mg, and this corresponds to the massive Vlasov equation. Okay? Solution to Einstein-Vlasov system is a triple Mg-F, and in particular, the stationary vacuum solutions that I showed you in one of the previous slides, so Minkowski, Schwarzschild, and Kerr, they solve coupled with a trivial F, meaning F identically vanishing, they solve the Einstein-Vlasov equations. But now in the massive case, and this again was said by Jacques already, so in the massive case, it turns out that there exist non-trivial, meaning solutions with non-identically vanishing F, non-trivial static spherically symmetric black hole solutions to the Einstein massive Vlasov equation bifurcating from Schwarzschild spacetimes. So this is due to Rhine and Jabiri. So these are in fact smooth solutions where F is compactly supported. So similarly, it happens for Kerr spacetimes. So there exist now stationary axisymmetric black hole solutions to the Einstein massive Vlasov equations bifurcating from Kerr spacetimes. Okay, let me note that in fact, for the massive Vlasov equation on fixed Schwarzschild spacetime, already admits an infinite dimensional family of non-trivial stationary solutions. So this again was said by Jacques. So the behavior, of course, the Vlasov equation being a transport equation along the geodesic flow, the behavior of solution is very much dependent on the geometry and the structure of the geodesic flow. And in particular, the existence of the stationary solutions to the massive Vlasov equation on Schwarzschild is due to the presence of bounded time-like geodesics that do not cross the event horizon. Okay, so in particular, for increasing values of the conserved angular momentum of the geodesic, you can find a curve in the radial potential governing the radial motion of the geodesic, which allow for bounded sort of motion around the local minimum of the potential. Okay, so this I'm drawing is the potential, the radial potential for time-like geodesics for the Schwarzschild spacetime. Particle mass 1. So the potential is asymptotic 1. Okay, so this should be put in contrast with the massless, in the case of the massless, or if you want the null geodesic flow, where the potential can only admit a local maximum, and you have this phenomenon that we typically call unstable trapping. And the Einstein massless Vlasov equation, they do not admit these bifurcations of this type that I describe on this slide. Nonetheless, there exist sort of large data deviations from Schwarzschild spacetimes, if you like, which give rise to static solutions to Einstein massless Vlasov equation, and this is due to some works by Andrew Hanson. But this won't be sort of directly relevant for what I'll be saying before. Questions? No questions. Okay. Now, crucial. Let me go back to the stability problem and summarize what is known about the stability of stationary solutions to Einstein-Vlasov. So in the case of Minkowski space, there are results by spherical symmetry by the Fermons proving nonlinear stability of Minkowski space as a solution to Einstein massless Vlasov. And later independent works by Taylor and Bigorn, Feynman, Judius, Mulevich, and Thaler proving nonlinear stability outside of symmetry. In the massive case, there's work by Ryan and Randall in spherical symmetry, and later work by Lindblad, Taylor, and Feynman, Judius, Mulevich, who independently prove nonlinear stability outside of spherical symmetry. Now, what about the Schwarzschild solution? So stability, the only nonlinear stability result known for this solution is this work by Veloso and Ruiz that Jacques sort of alluded to in his talk, in spherical symmetry, proving nonlinear stability of Schwarzschild as a solution to the Einstein massless Vlasov equations. Okay, and here in this picture, one expects stability even outside of spherical symmetry. Now, on the other end, because of the existence of these stationary solutions that I mentioned before, non-trivial stationary solutions that I mentioned before, one expects that in the Einstein massive Vlasov case, the picture is much more complicated, and in particular, you can only hope to converge to one of these non-trivial stationary solutions via a more complicated mechanism than the stability mechanism that you would observe in the massless case. And this has to do with this mixing phenomena that Jacques described in his talk. Okay? And let me again mention this work by Chaturvedi and Luke for the non-relativistic case for the Vlasov-Poisson system, where they that you may view as a sort of non-relativistic analogy pointing towards the understanding this problem here in spherical symmetry, if you like. Okay. Now, a crucial ingredient in the understanding of the nonlinear stability of Schwarzschild as a solution to Einstein-Vlasov is the study, is sort of understanding decay for the Vlasov equation now as a linear equation on a fixed Schwarzschild spacetime. So here I want to summarize results in this direction. So in the massless Vlasov equation, there are works by Weissenbacher, Veloso, Ruiz, and Bigorn, Veloso, Ruiz proving decay to zero of the energy momentum tensor associated to F. So here, remember, the Vlasov equation is a transport equation, so F will be transported along the geodesic flow. So the natural quantity for which you want to show decay is the energy momentum tensor or components of the energy momentum tensor. And in these works, exploiting the unstable nature of the null geodesic trapping, they show exponential in time decay for the energy momentum tensor. Let me also mention work by Anderson, Blue, and Judieu proving a degenerate integrated decay estimate in the case of slowly rotating curved spacetimes for the massless Vlasov equation. And there is upcoming also work by Bigorn and Veloso, Ruiz studying the massless Vlasov equation full subextremal curved spacetimes. Now, in the case of the massive Vlasov equation is different, again, because of the existence of stationary solutions. One in general does not expect a general decay statement for solutions. There is results by Veloso, Ruiz proving decay to zero of the energy momentum tensor for dispersive F, meaning for the largest family of Vlasov fields F, which are not supported on those bounded time-like geodesics that I referred to before. Or if you want, conditionally to the fact that T, the energy momentum tensor associated to F, decays to zero. Okay? So let me comment maybe on this. So here the results shows decay, polynomial decay in tau, and this decay rate sort of rises. So it's lower than the Minkowski rate for the massive Vlasov equation on Minkowski, and it arises by the existence of geodesics which can travel away from the event horizon for arbitrarily long time before turning back and crossing the event horizon. So in particular, this can really be understood as a decay rate in a bounded area region. So you see this effect already in a bounded area region on Schwarzschild. Okay? So this phenomenon is sometimes called parabolic trapping. Okay? And it is the one determining this rate that you see here. And let me also mention this series of works that also Jack mentioned in his talk, where they analyze and they study the dynamics of laser fields, which are now supported on this bounded time-like geodesics around the minimum of the radial potential. Okay. So this was my review of the 3+1 dimensional case. Questions? Okay. So let's move on to the higher dimensional case, which would be, for today, would be 4+1 dimensional. So the Einstein vacuum equations in higher dimensions, they govern higher dimensional general relativity, which is, it seems to be of some relevance for theories of theoretical physics, which are formulated in higher dimension and for which you need to embed to gravity. They admit, as in the case of 3+1 dimension, they admit explicit stationary asymptotically flat solutions. So as you will see, all these solutions that I'm listing, they're all explicit matrix that one can really write down. So again, you have a high-dimensional version of Minkowski space and a high-dimensional version of the Schwarzschild solution that is called Schwarzschild-Tangerlini solution that is due to Tangerlini from 1963. So this is a direct generalization of Schwarzschild. You have a Kerr high-dimensional version of Kerr black holes that are called Myers-Perry solution, Myers-Perry black holes. They were first formulated in the 80s in 1986 by Myers and Perry. And then there is a new completely independent family of black holes, which has no lower dimensional correspondent version, which is called the family of black rings. It's originally discovered by Emparani and Reali in 2002. So Schwarzschild, Tangerlini, Myers-Perry, and black rings, these are all black hole solutions and are the black hole solutions that I will talk about, excluding for today's talk, the last family of solution, black rings. Find them very interesting, but for today, I would like to say something about the other ones, okay? Okay, so very quickly, this is Schwarzschild-Tangerlini, metrical Schwarzschild-Tangerlini solution. This we saw in Sam's talk. Again, one parameter family of static, spherically symmetric, and asymptotically flat solutions. For m equals 0, you recover back Minkowski space. So I'll be looking, so you see that here you can really formulate for any dimension higher than 3+1. Okay, so again, as in the 3+1 dimensional case, there is a high dimensional version of Birkhoff's theorem that states that any spherically symmetric solution to the vacuum equation is again isometric to a Schwarzschild-Tangerlini solution for some mass. So again, spherical symmetry, even in higher dimensional, implies no dynamics. Implies that you are static. So the Schwarzschild-Tangerlini family sits within this more general family of rotating Myers-Perry solution. That is now a 3-parameter family of solutions, where the parameters are called A1, A2, and M, which satisfy this sub-extremal relation, sub-extremal range, which are slightly simplified from the actual one, but we won't lose any information from looking at the relation in this way. So A1 plus A2 is strictly less than M. So this is a family of stationary black hole solutions with spherical topology, meaning that, for instance, the intersection of a Cauchy hypersurface with the horizon will be a topological 3-sphere. So it's a spherical black hole solution. It is biaxially symmetric. So now in 4+1 dimensions, solutions cannot meet 2 independent axes of rotation. And the solution will be symmetric relative to both the axes. They're asymptotically flat in the usual sense that you know. So in particular, if you set A1, A2, and M equal to 0, you recover 4+1 dimensional Minkowski. And the case A1 equal A2 equals 0 corresponds to the 1-parameter family of 4+1 dimensional Schwarzschild-Tangerlini solutions. So here you see on this diagram, you see the allowed black hole parameters. So in particular, let me stress that, so this point corresponds to the Schwarzschild-Tangerlini solution. So these regimes will be singly rotating. The ones on the axis will be singly rotating regimes, where one of the two angular momenta is equal to 0. There's another special regime that in some cases sort of simplifies the problem a lot, which is the one of equally rotating Myers-Berry black holes, let's say, where A1 is equal to A2. And this line will be the extremal members of the family. Okay, and the area, if you like, is fixed by the mass of the black hole, the area of this sort of triangle. Okay, now contrary to the case of curved black holes, there's no rigidity conjecture precisely because we know about the existence of black rings, okay, which are independent from this family. Okay, now let me get into stability of these black holes. So there's only one nonlinear stability results for what concerns the vacuum Einstein equations for higher dimensional black holes. And this is very early work by Olszegel and then the Fermos Olszegel that proves nonlinear stability of the Schwarzschild spacetime as a solution to the Einstein vacuum equations in 4+1 dimensions. So this is a problem done under a 1+1 dimensional symmetry reduction in a symmetry class, which is more general than spherical symmetry and which allows for two dynamic degrees of freedom. Okay, sometimes called biaxial Bianchi 9. So other than this result, there's no other nonlinear stability results for higher dimensional black holes to the best of that are known, or to the best of my knowledge. So the expectation is that Myers-Berry black holes as solutions to the vacuum Einstein equations, they would be nonlinearly stable, again, as solutions in the vacuum case. Whereas what I will try to explain today, perhaps one should expect that the dynamics of Myers-Berry black holes as solutions to the Einstein massless Vlasov equation will again be similar to those of curved black holes. But on the other hand, in the case of Einstein massive Vlasov equations, there will be some significant differences. And this would arise already in the case of higher dimensional Schwarzschild. So in the case A1 equal A2 equal to 0. Okay. So as a preliminary step towards understanding sort of these two comments and these two problems, it is, as it was done for curved black holes, one wants to start by understanding decay for linear fields on fixed Myers-Berry black holes, for which very little is known if compared to the problem of curved black holes. Questions? Okay. Now, before moving to considering some linear fields and telling you what one really wants to understand, I have a slide about the geodesic flow of higher dimensional black holes. And this really will be, I think, the main slides of the sort of the main idea of the talk, the main slide of the talk. So like in the case of curved black holes, the geodesic flow of Myers-Berry black holes, it is completely integrable. Okay, so you can, in particular, separate and study the radial motion as a one-dimensional problem, if you like. Now, here are two important properties of the geodesic flow. So all Myers-Berry black holes admit no quotation mark stable trapping of null geodesics. So this means that, like in the case of curved black holes, the radial potential corresponding to null geodesic motion can admit at most one critical point, and this will be a local maximum of the potential. Okay, so this is like in the case of curve. The second property is in contrast with curve, and it has to do that now in the case of time-like geodesics, again, the potential can admit at most one critical point, and this critical point will be a local maximum of the potential. So in other terms, you cannot have any stable trapping of time-like geodesics in the case of Myers-Berry black holes. Is it clear? Yeah, okay. And this already sort of arises, as you can already see, in the case of higher dimensional Schwarzschild. So the picture that you see here is for 4+1 dimensional Schwarzschild black holes, the plot that you see, where for zero angular momentum, if you like, you will have a curve like this, asymptotic 1. For increasing conserved angular momentum, you will have these gray curves that you see on the picture. And then for the angular momentum above a certain critical value, you will have the top curve that you see in the plot. So you only have one critical point that will be a local maximum. Okay, so if you forget for a second about Myers-Berry black holes and we only think about higher dimensional Schwarzschild, these properties remain true for any higher dimensional Schwarzschild black hole. But one sort of curiosity about the number of dimensions, which I didn't appreciate before, is that in the case of n greater or equal than 5 plus 1, meaning starting from 2 dimensions higher and above, the only geodesics which do not have a critical point are those with L equals 0. So for any positive L, you will have a curve like the one that you see on top. Okay? Okay. So now, what I want to explain is sort of how this ingredient and this sort of property affects and sort of contrast with the properties of linear fields on these black holes as compared to Kerr, or to Schwarzschild, if you like. So first slide would be about the Vlasov equation. So again, we want to look at the Vlasov equation on fixed Myers-Berry black holes and prove decay. Now, in the case of the master's Vlasov equation for Schwarzschild, meaning A1 equal A2 equals 0, there is upcoming work in collaboration with Flavio Rossetti, where we prove decay to 0 of the energy momentum tensor with an exponential rate. So this, if you like, both the nature of the statement and the properties that you exploit will be very similar to what you see for the 3 plus 1 dimensional Schwarzschild case. And there is ongoing work by a graduate student at GSSI, graduate student of mine, Anja Lauri, where she looks at the case of the master's Vlasov equation, but now on Myers-Berry black holes. Okay? So here again, let me stress, in this picture, you expect something similar to the Kerr picture. Now, in the massive case is where you see a difference. So in the case of A1 equal A2 equals 0, so 4 plus 1 dimensional Schwarzschild, in upcoming work with Flavio, we prove unconditional decay to 0 of the energy momentum tensor. So here, because of the absence of these bounded time-like orbits that were present in 3 plus 1 dimensional Schwarzschild, one doesn't have to worry about the presence of stationary solution to the massive Vlasov equation. Okay, so in particular, you can prove an unconditional result without having to restrict to the dispersive Vlasov fields, okay, without having to restrict to the solutions that you consider. So in particular, we prove a polynomial decay of the energy momentum tensor that you see on the slide, where the exponent of, if you like, the rate of decay, it depends on the concavity of this parabolic trapping of this curve that I showed you before on the slide. So that's where arises the dependence on the number of dimensions in the decay rate. Okay, whereas the case for Myers-Berry black holes remain perhaps for future works. And again, in the future, one maybe wants to understand how this different picture in the massive case that already arises for the massive Vlasov equation of fixed background, how this enters maybe in the nonlinear problem already for the stability of high dimensional Schwarzschild as a solution to the Einstein massive Vlasov equation. Okay. Do you have any questions? No questions. Okay. Now, let me also, for completeness, to tell you something about the wave equation. The wave equation, like in the case of Kerr black holes, is fully separable on Myers-Berry black holes. And there are very few results known about linear waves on Myers-Berry black holes. There's 2 papers about high-dimensional Schwarzschild black holes by Schlue and Laut-Metcalfe proving polynomial decay for the wave equation on high-dimensional Schwarzschild. And there is another result by Laut-Metcalfe, Tikar and Toneanu proving an integrated decay estimate on slowly rotating Myers-Berry black holes. So this would be Myers-Berry matrix close to the origin of this plot that I showed you before. And then there is a mode stability result, which is quite recent, for the wave equation in the full sub-extrema range. Okay, so like in the case of curve here, one expects that one expects uniform boundedness and polynomial decay for general solutions to the wave equation in the full sub-extremal range of Myers-Berry black holes. And let me also emphasize that maybe understanding the Masters-Vlasov equation on these spacetimes may be viewed as sort of an intermediate or preliminary step towards then maybe studying the more complicated wave equation. Okay. Now, last slide. It's about the Maxwell equations on Myers-Berry black holes. So the Maxwell equations can, in a way, be understood as a intermediate step between the wave equation and the linearized Einstein equations, in that you now dealing, instead of dealing with a single scalar equation like for the wave equation, you now deal with a system of linear equations. Okay, so the Maxwell equations can be formulated as a first-order system for components of the Maxwell tensor F relative to a certain null frame that you would have to choose on Myers-Berry black holes. Now, I claim that there is a convenient choice of this null frame on Myers-Berry black holes that is called the algebraic special frame of Myers-Berry black holes, which has a Kerr analog, which I'll describe in a minute, and relative to which you can define your Maxwell unknowns, alpha, alpha bar, rho, and sigma, as you see on the slide, and understand these unknowns as tensors over the orthogonal complement of the span of E3 and E4. So this would be the horizontal distribution over which these quantities are defined. And it is a property of this algebraic special frame that this distribution on which you define your unknowns will be a non-integrable distribution in the sense of differential geometry, meaning that the commutator of the basis of this distribution won't be closed under commutation of the vector in your basis. Okay, so this is something that you can also do and has been done on Kerr spacetimes, where you can choose the algebraic special frame of Kerr to define your Maxwell unknowns. And again, you run into this complication of having to deal with horizontal non-integrable distribution, but now gaining at the advantage of the following property, namely the fact that the two extremal Maxwell components, alpha and alpha bar, they will decouple from the rest of the Maxwell system and satisfy the spin ±1 Tarkovsky equations, which you can then analyze independently from the system, and then go back to the system and control rho and sigma, exploiting your prior control on alpha and alpha bar. Okay, and this is somewhat the approach followed in these two works that I mentioned here by Pasqualotto and Teixeira da Costa and myself in the Schwarzschild and full sub-extremal Kerr cases, respectively. There are also other works exploiting this idea in the Newman-Penrose language as well. On the other hand, by formulating the system in this way, for the Maxwell equations of Myers-Berry black holes, one will have to dispense with the Tarkovsky decoupling for alpha and alpha bar. So it is known, and this was actually briefly mentioned by Sam in the previous talk. So it is known that even relative to the algebraic special frame, already in the Maxwell case, the extreme Maxwell components, they do not decouple into spin 1 Tarkovsky equations. Or in fact, they do not decouple into any decoupled equation from the rest of the system. Okay, and this was observed in the language of Newman-Penrose quantities, was already observed in these works by Godazar and Darky and Rial. These were mentioned by Sam as well. Okay, so in the case of A1 equal A2 equals 0, so in the Schwarzschild case, so it turns out that there is still a residual, here I call it a Faccarelli-Ipser type decoupling of rho and sigma. So there is a residual decoupling of the two middle components, which can in fact be decoupled into two separate wave-like equations and analyze separately from the rest of the system to then go back to the system and control alpha and alpha bar. And this is what is done in upcoming work by Pierfrancesco Martini, who's also a graduate student at JSSI. In the case of Myers-Berry with A1 and A2 non-zero, one also has to dispense with this residual residual decoupling of rho and sigma. So now it's really the case that none of the quantities appearing in the system will decouple from the rest of the system. Okay, so there is something more that one has to understand, and this is subject of ongoing work by Pierfrancesco. Okay, so the failure of this Tarkovsky decoupling will persist in the case of the linearized Einstein equations. So if you like, this Maxwell problem is, in this sense, sort of a step to then maybe understand the failure of this decoupling in a more complicated case of the Einstein equations. And in the case of high-dimensional Schwarzschild, sort of this residual decoupling of the middle quantities in the Maxwell case as a reflection in the decoupling of some quantities into Reggie-Wheeler type equations in this work by Keller and Wang about the linear stability of high-dimensional Schwarzschild black holes. Okay, so this is all I wanted to say. I think I went. Do we still have 10 minutes?
Yes.
Okay.
With questions.
Maybe I can take questions, and then if I have sort of some more time left, I will say something more. Okay.
Let's take questions now.
How much time do I have?
I mean, totally have another 12 minutes, including.
Okay. Okay. So then I have one more slide about yeah, I don't remember if it's supposed to be 50 or 60 minutes.
It's 60 with the questions.
Okay, then I'll do 50. Okay. So I have an aside about the family of black holes, which I said I would ignore in this talk, but now, because I have time, we won't ignore, which was this family of black ring solutions. Okay. So this is a, let me recall, this was a explicit metric, stationary matrix of stationary asymptotically flat solutions, which are again biaxially symmetric in the sense that I explained before. But now they are completely independent from this other family of Myers-Berry solutions in the sense that now the event horizon has a different topology than the one of Myers-Berry black holes. And it has this ring type topology as 1 times S2 when you intersect the event horizon with the Cauchy hypersurface. Okay, now, as I emphasized before, these high-dimensional black holes can have sort of very different properties from the point of view of the geodesic flow. So in the case of these solutions, the surprising property is that some of these black rings, maybe this here, I mean some members of this black ring family, that admit stable trapping for null geodesics now. Okay. And this is something I've actually observed already in my PhD thesis. So some interesting question. One interesting question that maybe one could think about is the effect of this null stable trapping in the case of the massless now Vlasov equation on fixed black ring backgrounds, and then maybe more ambitiously trying to maybe understand what could be the dynamics of these solutions as solutions to the Einstein massless Vlasov equations. Okay. You have a question? No, no question. Okay. Another question has to do with the behavior of general solutions to the wave equation on these black rings admitting stable trapping of null geodesics. So there is work of mine where I prove that solutions to the wave equation, they exhibit this following property. So either uniform boundedness fails, or if it holds, that will only decay logarithmic in time. Okay, so if uniform boundedness holds, then by some general, it's actually a general result by Yorgos Moskidis, that we know that if uniform boundedness holds, then you will at least decay logarithmic in time. And what I've shown in this work is that actually this logarithmic decay, in the case of these black rings, is sharp. So you can really only decay logarithmic in time. So what remains open is this dichotomy that doesn't clarify if uniform boundedness really holds or not. Okay, and this is sort of interesting and maybe a future question that would be nice to understand. And this is a related work by Yakov and Toneanu, which which in a way has to do with the strategy and the technique that you might want to use to approach this uniform boundedness problem in the case where you do not expect to be able to prove an integrated decay estimate. Okay, proving uniform boundedness in the case of Kerr, you typically prove first integrated decay and then establish uniform boundedness. Whereas in this case, because you know that if uniform boundedness holds, you only decay logarithmically, you won't be able in the first place to prove integrated decay. If that makes sense for you. Okay, perfect. And also, so the questions have to do with the nonlinear effect of this slow linear decay. I have some numerical work with Cardenas, Avendano, Pretorius, and Sullivan, where we look at some model spacetimes where stable trapping for null geodesics is present, and we study the dynamics of nonlinear waves on this fixed background. And there's also an analogy and works in the case of asymptotic ADS black holes, where the stable trapping of null geodesics is also present because it's low decay of the linear wave equation on these spacetimes. And then it is there also open and interesting to understand what the effect of this low decay will be for the nonlinear dynamics already at the scalar level, where there is recent work by Kere and Moskidis on nonlinear waves on fixed structural ADS backgrounds with reflective boundary condition and some numerical simulations by Pau and Rossi. I think I'll stop here. Thank you very much.
Thanks.